In this video, we're going to really get into the calculus. We're going to talk about the definition of the derivative. So we're going to be starting with the idea of instantaneous rate of change of a function. And much like when we talked about, the introduction to calculus, we were talking about the car with the broken speedometer, we're going to find the instantaneous rate of change of a function by computing average rate of change over smaller and smaller intervals. Now that we're equipped with the idea of a limit, you can see that's going to be coming into play here. Okay, to give you a recap of that, if we took the average rate of change of a function, you can see on the right that that dotted line is somehow capturing the behavior right in that moment. Okay, the average rate of change, which you're seeing to the left, isn't doing as good of a job. And there you can see my very low-tech idea of showing you the red point moving closer and closer to the black point, the limit as run approaches zero of rise over run. Now we knew in Algebra 1 that the slope of a line segment was computed using rise over run, and we saw when we talked about average rate of change in the last lesson that it was still the same thing. We're just going to be interested in rise over run on really, really small intervals. And when possible, we're going to try to take the limit as run goes to zero and just see what happens. Okay, and so this is going to be our definition of the instantaneous rate of change. AP Calculus, we don't actually need to work with that limit definition all that much. What we need to be able to do is recognize that limit in a problem and realize that it's kind of a coded word for slope. Okay, so consider the piecewise function f defined below. F of x is a parabola sometimes and a line other times. So what's the value of the limit as h approaches 0 of f of 1 plus h minus f of 1 all divided by h? Okay, this is a limit of rise over run as run goes towards 0 with x equals 1 plugged in. Okay, so, or maybe we said c equals 1 up above. Okay, so this is going to be the slope of the graph of f at x equals 1. That apostrophe, we read that as f prime of 1. And so we're going to say f prime of 1, that is the slope of f at x equals 1. We're going to look over here on the graph. We're going to see, okay, it looks like the slope right there is horizontal, and we know that the slope of a horizontal line is 0, so we're going to say that equals 0. The next one asks us about the value of the limit as x approaches 3 of f of x minus f of 3 over x minus 3. And it's like, this is a little different. We don't have a definition for this. But look at it. It looks like the average rate of change. And that's rise over run. And what's happening to run in the denominator? Run's going towards 0. So it's like, this is just another version of the limit of rise over run as run goes towards 0. So that must mean the instantaneous rate of change of f at x equals 3. Now, I should probably also show you like the alternative form of the definition of instantaneous rate of change. But I like the h one better because it's closer to what I always try to remind students of, which is the limit of rise over run as run approaches 0. Okay, so we're talking about f prime of 3 here. And we're thinking about the slope of the graph of f at x equals 3, so the slope of that line segment, it's like, well, we don't really have a grid, so we're going to go default over here to the equation. And thinking all the way back to Algebra 1, we had y equals mx plus b. It was m that represented the slope, so we know that the slope of this line is going to be negative 1.5, so that's f prime of 3. Ask if the value of f prime of 0, so that's like the slope of f at x equals 0, is that positive, negative, or 0? Yeah, and because this thing is curved, we don't really exactly have the tools yet to figure out what that's going to be. Alright, so slope of f at x equals 0. Well, we just look over there, and the graph is going downhill. The tangent line would have a negative slope, and so we're going to say f prime of 0 is a negative number. And then the next natural question is like, what's going on with the instantaneous rate of change of this function at x equals 2? We've got something weird going on here. I always ask students what they've got to say about it, and they've got a variety of descriptors for it. But I'd say we've got like a sudden change in the instantaneous rate of change. It was increasing, and the function f was increasing, and now it's suddenly decreasing. It looks like it's got a sharp corner on its graph. But we'll come to that in a minute. So I'm going to say it's suddenly changing. But I want to talk about the instantaneous rate of change of f, more algebraically in terms of like mathematically our definition that we took up above. We said it was the limit of rise over run as run goes towards 0. And if we're looking at a picture of a graph and we're talking about limit, we need to think about the two one-sided limits. Right? We're going to say, okay, well, the limit of rise over run as run approaches 0 from the negative side. Well, I'm not sure what it's going to be because we were working on a curved piece of graph, but I know it's going to be a positive number because the function was increasing. And then as run approaches 0 from the positive side, run to the right of x equals 2, well, I've got the linear piece of graph. And so the limit of rise over run as run approaches 0 from the positive side, I think is going to be negative 1.5. And while I don't know what the purple number is, the positive number, I know if it's positive, it can't be equal to negative 1.5. And if the two one-sided limits disagree, we're going to say that the limit generally does not exist. The limit of, as run approaches 0 of rise over run, that fails to exist. And as a result, okay, that's the definition of f prime of 2. We're going to say f prime of 2 does not exist either. And that sharp corner is going to be kind of the official nomenclature we take in this class, but we'll have more to say about this here in a second on the next page. We're going to talk about a new vocabulary word to us, differentiable. So a function is going to be differentiable if that instantaneous rate of change exists at that point. Okay, and a synonym for differentiable would be smooth, and that's, I think, something you can kind of picture on the graph, not having any sharp corners or anything like that. Okay, so we've got two examples of functions that are not differentiable at points, and I'm going to show you why that's the case, and then we will list out the reasons a function might not be differentiable in this class. Okay, so first would be f of x equals 1/3 of the absolute value of x. We've seen this graph before. Okay, it makes a v. Okay, and if we think about it, okay, yeah, that's having a sharp corner right there at the origin, so why it's not differentiable at x equals 0, it's just like we saw in the other one, sharp corner. Okay, the graph of f has a sharp corner at x equals 0. Always best to be specific with our explanations. Then, the graph of y equals cube root x. Now, that's one you might not have thought about recently, but I'll sketch you the graph of it. And think about the tangent to the graph of g at x equals 0. If you were to lay it in, it looks like the y-axis is tangent. And differentiable is that instantaneous rate of change, which represents the slope of the tangent line. And so I'm thinking that that's going to be a vertical tangent, and the slope of a vertical line is infinity. So we've got there not differentiable at x equals 0 because of that vertical tangent. So the graph of g has a vertical tangent at x equals 0. Okay, so that's two of the three reasons why a function might not be differentiable, right? We might have a sharp corner, which could look something like this. We could have a vertical tangent, which in this class frequently happens when you join two semicircles together. Just going to point that out. That's a very, very frequent cause of vertical tangent. And then also the third reason we could have non-differentiability would actually be any discontinuity in the graph of the original function. Okay, because if you just think about a function that's got a discontinuity like that one, okay, where would you put the tangent there? And it can't, you got to be tangent to the graph at the point of tangency, and it's like, where would you lay the tangent in if there was no graph? Okay, and there's also, algebraic reasons in the limit why it wouldn't exist. In this case, f of c itself doesn't exist, so that would make the limit tough to compute because one of the ingredients doesn't exist. Okay, now if any discontinuity causes a function not to be differentiable, it's going to be equivalent to say if a function is differentiable, then it must be continuous. And I don't want to get too much into the logic of the contrapositive and stuff right here, because that's not really what the focus of AP Calculus is. I'm just going to point off to the side that the related theorem that you do need to know is that if a function is differentiable at a point, then it must be continuous at that point. And I have proved this on video before. If you're interested, click up at the top. I'm sure I'm displaying it right now. But we're not going to be proving that in this video. All right, now a very common question type for our class is going to be like, hey, here's the graph of a function. Tell me the values where the function is continuous but not differentiable, or just fails to be differentiable. Okay, but in this case, if we're looking for continuous but not differentiable, that's going to be the first two types, right? Because the third type was any discontinuity. So we're looking for places where we've got a sharp corner. So there's one right up there. Or possibly a vertical tangent. There it is, happening right there. So these places are, the graph is continuous but not differentiable because of these reasons that we just talked about. Okay. And I think I might as well, should have mentioned it up above, but the real reason why we're not differentiable at the point in red is because the limit of rise over run fails to exist because of disagreement in one-sided limits, whereas in blue, the limit of rise over run fails to exist because it's going to infinity, and infinity is not a real number. Okay, but I'll just report my x values, and then I'll just be ready to move on to the idea of the derivative of a function. Okay, so the idea of the derivative, and that's a word you've maybe heard before, at the very least at the very beginning when I was talking about the introduction to calculus. It's a function that reports the rate of change of another function. So we read that apostrophe again, that's f prime of x. It's the limit as rise over run, or as run goes to 0 of rise over run, but at any x, right? We don't have that c, which happens to usually mean some specific x value. So what I would say is that this f prime of x is a different function that reports the instantaneous rate of change, or the slope, of f at any x. Okay, now I don't want to waste a whole bunch of time on this, but it would be remiss of me not to show you how we can find derivatives of functions, especially easy ones, using this limit definition. Okay, we'll have better rules, in the lessons to come that will show us, like fast ways to compute these derivatives. But for now, all we have is the limit definition, the limit of rise over run as run goes towards 0. I'm going to actually start in the middle here with g of x equals 2x. I'm going to draw a picture of that. Okay, you see what that graph looks like. You've known this for a while. This is a line with slope 2. So that means that g prime of x, the function that reports the instantaneous rate of change, or the slope of f, or slope of g in this case, at any x, well, that should just always be 2 because that line slope is unchanging. Okay, so we should be able to apply this process here, this limit of f of x plus h minus f of x all divided by h, and get 2 back. So first we're going to need to find g of x plus h, so we have all of our ingredients. That's going to be replace x with x plus h everywhere we see it in the formula. Okay, that's going to be equal to 2x plus 2h. And so when I want to take the limit as h approaches 0 of g of x plus h minus g of x all divided by h, I'm going to be setting up, okay, and have a subtraction in the numerator. G of x plus h was that 2x plus 2h. And then I'm going to subtract g of x, which was 2x, and it's like, okay, the 2x minus 2x, those are going to go away. And then I'll be left with the limit as h approaches 0 of 2h over h, and we could cancel off those h's, especially when h was not equal to 0, which it's not if we're taking the limit as h approaches 0. H is just very near 0, and that's going to equal 2. Okay, so that's how we're showing that g prime of x equals 2 using the limit definition. For f of x equals 5. Okay, if we draw a picture of that graph, that is a horizontal line. Its slope is 0, so we would expect that f prime of x would constantly equal 0. Now, if we go in, and this is always tricky for people, but if we replace x everywhere we see it in the formula for f of x with x plus h, we're only going to be replacing it on the left side. Okay, there's no x in the formula on the right. On the right-hand side of the formula, there's no x. So there's nothing to replace with x plus h, so f of x plus h is still 5. And then when we take that limit as h approaches 0 of f of x plus h minus f of x divided by h, we're really taking 5 minus 5 over h. Well, that's 0 over h, and 0 over anything is going to be 0, and h is not equal to 0 because h is approaching 0. So I know that this limit is going to equal 0, and that's kind of getting us what we expected. Now, h of x, this is 2x plus 5. This is g plus f. Okay, that's what I want you to notice about this. So this brings up the question, can I get the derivative of the sum of the two functions by taking the sum of the derivatives. Is h prime going to equal g prime plus f prime? And the answer is yes. Okay, we're going to see why here in a second. Let's just graph y equals 2x plus 5. And if you think about how I transformed the red line to get the green line, I just shifted it up by 5 units. Okay, but the slope didn't change. The slope is still 2 everywhere. So I know that h prime of x needs to equal 2. So I'm seeing evidence here of the sum property, and now this is definitely not proof of that, but that's kind of a different discussion. We're going to take that property kind of for granted in this class. It's just going to be something we use so often, we're not even going to question it. So h prime of x is equaling 2 plus 0, the derivative of 2x plus the derivative of 5, and that's equal to 2. So, that's showing you what I needed to show you. Right, now we're going to sketch the graph of the derivative of the function, that's going to be a tricky exercise for you at first, especially while you're still accepting the nature of the derivative function, being something that just kind of like reports on the slope of something else. It's not something you're used to. All right, so if we're going to do that, we need to just think about the slopes at the different places on the graph of the original. So we've got the graph of f here, and that's what I'm going to start with. It's kind of 2 line segments. So the first piece, if I look at it, kind of colored in blue a little bit, I'm going to see that it has a slope of -2. Okay, so that means that f prime is going to be equaling -2 all along the same x values that apply to that segment of the graph of f. So that's to say all x that's less than 1. And so I'm just going to plot that in like that. And then I'll look at the other piece of graph. Okay, this piece of graph is horizontal, and I know that a horizontal line has slope 0. So I'm going to plot 0 for my derivative at all the x values where the graph of f is horizontal, which is to say all the x that is greater than 1. Okay, but then at x equals 1, if I look at the graph of f, I'm seeing a sharp corner. And remember, a sharp corner is a place where the function is not differentiable, which is to say its instantaneous rate of change or its derivative doesn't exist. So on the graph of the derivative, we'll see holes in the graph, okay, both empty circles. Okay, for g, the graph of g is curved, so we're not going to be exactly able to see, the actual values of the derivative, not at this point. We'll only be able to see positive, negative, or 0. And if you're doing that, or suppose you're working a multiple choice question on this same idea, you're going to want to start with the places where the derivative is 0. And the derivative is 0 anytime where you've got a horizontal tangent line. So that's these 2 spots that I've marked in yellow. And I'm going to plot those down on the derivative because those are going to be zeros of the derivative, places where g prime equals 0. So the graph of g prime will hit the x-axis. Then I'm going to look for places where the graph of g has a positive slope, and I'm seeing it right there in the middle. Okay, mark that in purple. It's got a positive slope, so everywhere between those 2 points, g prime will need to be positive. Okay, but while coming back to 0 at each of those 2 places. So I've got part of the graph of g prime right there. Then I'll think about where does the graph of g have a negative slope. That would be these 2 places. So that means on those intervals, I need to see g prime being negative. And so, we don't know too much, but it looks like, as I go off to the left and off to the right, the slope gets steeper and steeper. That's going to be what the graph of the derivative looks like. Now the message here, there is a message. If you look at the graph of g, that looks like a 3rd degree polynomial. And the graph of g prime, that looks like a 2nd degree polynomial. And that's just kind of a shadow of something we're going to see in the next lesson when we learn about the power rule. Now the last example I've got for you has to do with writing the equation of a tangent line. And this is going to be a really important one for us because this is the type of problem we have to solve a lot in AP Calculus, or really any Cal 1 class. So, we're going to give you the formula for the derivative and some information about the original function f of 2 equals 7. Write an equation for the line tangent to the graph of f at x equals 2. Now, I need to remind you about the point-slope form of the equation of a line from Algebra 1. That's super important. If you've got a point that you you know that's on the line and you've got the slope, you can uniquely determine the line, and you can use the equation y minus the y coordinate of the point you know is equal to the slope times the x coordinate of the point you know. So in our case, we've got the ingredients we need. We're going to start with the idea of let's find a point. They tell us that f of 2 equals 7. That means that the point 2, 7 is on the graph of f. For the slope, I'm going to need the slope, but I've got a formula for the derivative, and that's what the derivative tells me. It tells me about the slope of f. F prime of x equals 2x plus 5. Okay, if I plug in x equals 2, I'm going to get f prime of 2, the slope at 2, is equal to 4 plus 5, which is equal to 9. And if I've got a point and a slope, I'm ready to write an equation. So it's going to be y minus the y coordinate of the point I know, so y minus 7, is equal to the slope, which was 9, multiplied by x minus the x coordinate of the point I know on the line, which was 2. And there we go. We've written our first tangent line equation, and now we're really rolling on the calculus. So that's going to be all for this video. Thanks for watching.